Hello, everybody. This is going to be our second lecture on rotational motion. And one of the things that was kind of strange for most people when we talk about when we talk about rotational motion is something called moment of inertia. Now, you guys may remember that moment of inertia, is the is analogous to mass. Okay, now if you are going to move or like push an object, it's going to offer more resistance if it has more of a mass. Now, when it comes to moment of inertia, it's not just the mass, but where the mass is located. And we talked a little bit about that in the first lecture. And if you think about how much easier it is to rotate, let's say, a meter stick if you're rotating from the middle versus doing it from the end. It is harder at the end. 1 second. All right, sorry about that little interruption. So as we were saying, moment of inertia, I, is proportional to mass, but it's not just the mass, but where the mass is. So I've come up with a definition for moment of inertia. Now this is mine, so you might not see this in a dictionary, but it's a measure of the resistance of an object to its state of motion, right? That's just straight up inertia, but we're changing it because now it's rotational velocity or rotational motion, and it's a result of the distribution of mass around the axis of rotation or potential rotation, right? So this will make a lot more sense when we kind of see some concrete examples, which I'm about to do. So you guys, there are two definitions, and I talked about this. I talked about this on our last lecture, and that the first definition is the sum of the mr squared. And this is essentially if we have discrete amounts of an object. So for example, if we have, let's say, 1 kilogram that is a half a meter from an axis of rotation, and then let's say that we have a 2 kilogram object that, let's say, is 0.75, and then we have a third object, let's say, is 3 kilograms, and it is 1 meter, and all these things are going to be rotating about this point. So what would the moment of inertia of this collection of discrete masses, okay, what would it be? So we're just going to add up the 3 mr squares, all right? So we're going to have 1 times 0.5 squared plus 2 times 0.75 squared plus 3 times 1 squared. So we have a quarter, and then let me change pens here so it's a little more clear. So 1 times a half a squared is a quarter. 3/4 squared is 9/16 times 2 is 18/16, and then 3. So if we change these all to sixteenths, we're going to get 4/16 plus 18/16 plus 48/16. So we're going to have 70/16, which would be 4 and 6/16, 3/8. So 4.375. Okay, we could call that, we'll say 4.38. Now, what are the units? What are the units for a moment of inertia? And that is going to be kilogram meter squared. So this would be the I for this collection of masses. There's definitely a question that is essentially this simple in your problem set, the first problem set from this week. So again, it's pretty straightforward. Now, where it gets more interesting is if we have an object like this meter stick that we talked about last time, and we rotate it here versus here, okay? Now, this time we kind of have this transition of different amounts of mass as it goes here. What we could do is we could essentially cut this meter stick into all of these 1 centimeter sections, right? And then we could do this 100 times and add them all together. But we could also slice this into 1,000 or 10,000 or 1,000,000 or a gazillion. And when we start dividing things by a gazillion, essentially what we have there is a calculus problem. And this is going to give us the second definition of how to calculate the moment of inertia of an irregular object. And I'm going to erase this and get things set up here, so bear with me. All right, so we are back now. Our second definition of moment of inertia or calculation is going to be I is going to equal to the sum of the r squared dm. Okay. Now, essentially, if we think about the sum of the mr squares, here we got mr squared. Let me make this r a little more r-like. So essentially, it's the same thing, except we're going to take and add up all of the little tiny masses, okay? And that will give us our answer. So now we're going to have a rod of mass m and length l. So this is essentially like our meter stick. But now we are going to rotate it. We're going to rotate it about the axis in the middle, all right? So as we had in the center of mass problem from our last unit, okay, this equation right here is not in a differentiable form because r and m are not the same variables. So in the same manner that we did it in the example 911 on page 248, I believe, we're going to do this in a similar sort of way, and we will see how this goes. Then, as now, we are going to use lambda, which is going to be linear density. Now, like volumetric density, which is mass over volume, linear density is mass over length. Okay, so we can see here that is equal to mass over length. And we can do this is if we had a object like this meter stick, right? It would have a constant thickness and a constant width, right? So those would cancel out anyway. So now we just have this linear density, and you can make it into an area density, etc. Now, how we are going to make this dm is we are going to take a thin section here that is going to have a mass of dm, and it is going to have a width of dr. We're going to have a width of dr. Now, you guys, we could call that dx or dy or anything we wanted. It is a distance, right? And we're going to go from here to here. So I could just as well have put in dx there, but realize that that r squared would be a length and it would be differentiable. It would be differentiable. Okay, so now we are going to have dm over dr. This ratio, this little small bit to this little small width, is the same as the overall mass to the overall length. So they're equal, and that is equal to our linear density. So in the same way that we did in 911, we're going to say lambda dr is equal to dm. And now we can substitute lambda dr, and it can go into dm. And now we can have the integral of r squared lambda dr, and our lambda can come out there because that would be a constant, given that this would be a constant a constant density, okay? So now our lambda can come out, and now we are going to get the moment of inertia of our object is going to be lambda r squared dr, which is going to be differentiable. And now the actual calculus of this is differentiating a very simple term is really easy. So we are going to get r cubed over 3, okay? And we still have our constant out there. And we are also going to evaluate. We're going to evaluate this from the beginning to the end, okay? And this part is, again, a little bit tricky. Instead of going from here to here, because our axis of rotation is in the middle, we are actually going to go from negative L over 2 to positive L over 2, okay, because our point of axis is here in the middle. So we go back a half and forward a half, and we get a whole. All right, so now we're going to evaluate it from negative L over 2 to positive L over 2. And now we can say L cubed over 2 cubed divided by 3, okay, minus a negative L cubed over 2 cubed divided by 3, okay? So when we cube that negative, it stays negative. And this negative are going to make it turn into a positive. So we're going to have L cubed over 24 plus L cubed over 24. 1/24 plus another 24th is 1/12, or 2/24, which is 1/12. So we're going to have L cubed over 12, but we still have this lambda. And now we can kind of go back to seeing that our lambda is equal to m over L. And now we are going to substitute in there. And now this lambda becomes m over L. This L in the denominator is going to cancel out with one of the L's there. It's going to make it squared. So our I is going to be 1/12 mL squared. 1/12 mL squared. Now, if we just take a quick look, and what if we wanted to do it? What if we wanted to do it, for example, like we did in the lecture from last time, we wanted to do it at the end, right? So now our axis of rotation would be here, which would be 0. And now we would differentiate from 0 all the way out to L, okay? Now, all of the calculus for this would still be the same. The only difference would be our how we evaluated it. So instead of it being positive L over 2 from negative L over 2, we're going to go from 0 to L. And now we would get the result of L cubed over 3 minus 0. L cubed over 3 minus 0. We're still going to have this lambda, but we're still going to replace that lambda. So we're going to get m over L times L cubed over 3. We're going to get this to cancel out. So our I rotating about the end is going to be, I'll put this sort of down in here. That I would be equal to mL squared over 3. Okay. Now we can compare this about the end and about the middle, and we can see that it would be 4 times easier, okay, 1/12 versus 1/3 to go from the middle than to rotate from the end. Okay, so this is an example, I guess this is an example of how we would calculate the moment of inertia based on calculus, which is kind of a the distribution that's not specific points, but one merges into the other. Now, there is going to be a list. There's going to be a list of moments of inertia of regular objects on page 278, on page 278 in your textbook. And if you go and look on that, you're going to see some formulas for how to calculate that. For example, a disk would have the moment of inertia that would be equal to 1/2 mr squared. If you had a hoop, it's mr squared. If you had a sphere, it would be 2/5 mr squared. So those would be things that you're going to look for on page 278. And when you look at problems, you are going to use that. It might say a disk of 12 kilograms and a radius of 25 centimeters. So essentially, this would be a disk. And so you wanted to calculate the moment of inertia of this. Then you would just take 1/2 the mass times the radius squared, and that's how you would calculate it. All right. So what we're going to do now is we're going to combine this moment of inertia and things like a disk and a hoop or a ring, and we're going to see how this is going to change when we talk about calculations involving mechanical energy. So I'm going to set up a little race between these two objects, and in these two objects, they're going to roll down a ramp. Now, this disk has a mass of like 486 grams. This has a mass of 463 grams. That's about a 5% difference, so not very much. Also, the difference in radius is going to be 7.5 and 7.6. Obviously, not a huge difference as far as the percentage, which is even much smaller. So, what I'm going to do is change this angle here. We're going to have a little race here, and we're going to see which one is going to get to the bottom of the ramp first. So while I switch there, you guys can think about, is the disc going to move or is the hoop going to move? So I'll see you in a second. All right, so I hope you guys can see this well enough. So I've constructed this little ramp here, and now we have our disc and our ring, and we are going to set this up. Hello. And now we are going to let them go. So I'm going to get them right here. So when I pull this away, we can see. So pay attention to which one is going to be in the lead when it reaches the bottom of the ramp. On your mark, set, go. And I think you can see there that it was the disc that was winning. So now we're going to go back to the board, and we're going to talk about the mathematics that prove that that disc is going to be going faster. So here we go. All right, now we are back here up on the board, and we're going to start out here explaining this about calculating the mass, or how fast a block is going to slide down a ramp of height h. Okay, and what we're going to do here is we're going to make the coefficient of friction equal to 0. So we've got a frictionless surface. So obviously this is going to slide here. And the concept we're going to use is conservation of mechanical energy. As you remember from the unit that we did before. Okay, so we're going to have gravitational potential energy. Okay, so U being the symbol for potential energy. So U gravity, and you guys remember that as mgh plus kinetic energy, okay? And these are going to be the initial, and this is going to equal to potential energy final plus kinetic energy final. Our kinetic energy initial is going to be 1/2 mv initial squared, mgh final plus 1/2 mv final squared. Now, if we go back to here, if our initial velocity was 0, then we can see that this would cancel out. And if we say h is equal to 0 at the bottom, that means h would be equal to, at the top, would be that. That means this would go away. And our m's would cancel out. So we can see that v squared would equal to gh times 2, because the half would come up. We would take the square root. And so the velocity of a block on top of a ramp going down a frictionless surface, the formula would be the square root of 2gh. Okay, so velocity of the block is going to equal to the square root of 2gh. All right, so now, you guys, now we are going to change from a block to a ring. Okay, a block to a ring. Now, the moment of inertia of a ring, okay, and if we look on page 278 of your book, it will tell us that the moment of inertia is just mr squared. Okay, now if we think back to that formula for the discrete moment of inertia, here we have a mass, and all of the mass is the same distance from the axis of rotation, right? So that would just be the sum of the mr squared, all the same, all the mass and all the radius. So that is going to be our moment of inertia. So what we have to add, what we're going to add into our conservation of mechanical energy here is not just translational, okay? Not just translational kinetic energy. Now we're going to have, we'll call that linear kinetic energy, and we're going to have rotational rotational kinetic energy. All right, so we're still going to have mgh initial plus 1/2 mv squared. Now, in the last lecture, I told you that the kinetic energy rotational was 1/2 I omega squared, which makes sense because I, the moment of inertia, is the rotational analogy to m, and omega is the rotational analogy to linear velocity. Okay, so we have all this in the beginning, okay, and we're going to have mgh final plus 1/2 mv final squared plus 1/2 I omega final squared. And again, if we start out with an initial velocity of 0 like we did, these two things are going to cancel out. Our gravitational potential energy, h, is going to go to 0. So we're going to end up having mgh is equal to 1/2 mv squared plus 1/2 I omega squared, 1/2 I omega squared. So we already said that our I for a ring, okay, is going to be mr squared. So we can substitute in here mr squared. And you may remember from last lecture that the relationship between linear velocity and angular velocity is r, okay? So if we have a wheel that's moving translationally, the angular velocity times r will equal our linear velocity. Now, if we divide both sides by r, okay, then omega is going to equal to v over r. So now we're going to put in v over r. They are going to get squared. And now we can see that the r squares cancel out. Not to mention, we have the m's cancel out. We're going to have a half plus a half is a whole. So we're going to have v squared is equal to gh. We're going to take the square root, and we're going to get the velocity of the ring is equal to the square root of gh, the square root of gh. Okay, so now, again, if we had a frictionless surface, we would see that a block sliding down a frictionless surface would be 41% faster, okay? The square root of 2 is 1.41, and the square root of 1 is 1. Therefore, it would be 41% faster. So 1.41 versus 1. Now, you guys, we're going to do this a third time, okay? But now we're going to make this a disk. And the I for a disk, and again, this is on page 278. You could do this with calculus by making the calculation using the integral of r squared dm, but you would end up with 1/2 mr squared, 1/2 mr squared. Now, without really erasing too much here, we can see that this one right here would be the I for the disk, and that would be 1/2 mr squared, 1/2 mr squared. Now, those r squares would still cancel out. But now we're going to have a half of a half, which is going to be a quarter. So we're going to have 1/2 plus 1/4 v squared, which is going to be 3/4 v squared is equal to gh. And now we're going to move this to the other side. We're going to get 4/3. We're going to take the square root. And the velocity of a disk rolling down a inclined plane, the velocity at the bottom is going to be equal to the square root of 4/3. So velocity of a disk is going to equal to the square root of 4/3 gh. Okay. Now, if you take the square root of 4/3, you're going to get something close to 1.15 versus 1, the square root of 1, which is 1. Essentially, what we have here is that our disk, our solid disk versus our hollow ring, same mass, same radius, this is going to be 15% faster. If you think back to the, our little demonstration there on the inclined plane, you can see that the disk was slowly getting farther and farther ahead, and we could measure that, but about 15% farther sounds reasonable. Okay, so we could do something with a sphere. If we had a ball, and the I for a sphere, and again, you're going to look this up on page 278, and you're going to have 2/5 mr squared, and you could put in 2/5 into that equation, 2/5 instead of 1/2, and you're going to see that if we had a sphere there, it would also be a little bit faster. Okay, I'm going to set up for our next part of our lecture here, which is going to be on torque. So, all right, for this next part, we're going to do a kind of a quick review. This is going back to our second quarter last year. And if we have two objects moving around a disc or a pulley that is massless, right? So our first example is we're essentially going to ignore this. But what we're going to have here is this 1 kilogram mass is going to pull down, and it's going to move this 5 kilogram mass to the left, and they're going to move together. So what we're going to do is we're going to calculate what the acceleration, we're going to calculate the acceleration of these objects. This is going to set us up for talking about torque. Okay, so now since we have two things, we're going to have this, if this were not attached, right, and we were to drop this object, this would fall due to the force of gravity. It would have an acceleration of 9.8, right? So what we're going to do is we're going to take the sum of the forces of this object right here, which is going to equal to ma. Now, obviously, we are going to have the fact that there's going to be the force of gravity that is pulling that down, right? But we also are going to have this tension in the rope is going to be pulling up, right? So I'm going to say down is positive, and so we're going to say mg minus t is equal to ma. Now, we can, since I made this mass 1, okay, we can just say g minus t is equal to a. If this mass is different, then we couldn't do that. Now, we're going to go back to this right here, okay? Now, if this is on a frictionless surface, this tension here is going to be pulling to the left, and this tension are the same. They're just pulling in opposite directions like any string or rope would. So when we go to the sum of the forces on this one, okay, there is only one force. There is only one force, which is pulling to the left because there's no resistance force. Friction is 0. And that's going to equal to ma. But now this is going to be 5a because I made that mass 5. Okay? So now we can now plug in this t into here. So now we can say 9.8 minus 5a is equal to 1a. 9.8 is going to equal to 6a. We divide by 6, and our a is going to be about 1.67, okay? So 9.8 divided by 6, 1.63. 1.63, not 1.67. Okay, so our acceleration would be 1.63 meters per second squared. All right? Now, obviously, if this is lighter, then the acceleration would go up, and if it was heavier, okay, then this force here would have to move more mass, and therefore the acceleration would be less. So this is where we're going to go into a transition, is we are going to get rid of this mass right here, and we're going to say that this now is no longer a massless pulley. We are going to say that now this disc, this pulley, is going to have a mass of 5 and a radius of r. Okay, so essentially we're going to have the same sort of setup here. So now this rope is attached to the pulley. So all of this part is going to be the same. Okay, so I'm just going to get rid of the here. Okay, and now we are going to change, you guys, we're going to change from this being a force to a torque. Okay, so remember that torque is equal to force times the perpendicular radius, force times the perpendicular radius. And whenever you have a rope on a spool, then the perpendicular radius is going to be the radius of this, right? Because if we move it up like here, that's still going to be at 90 degrees because the rope is always going to be touching tangentially, and the tangent to the radius is going to be 90 degrees. So whatever our force is times our radius. Now, remember, our force here is going to be tension. So tension times radius, I already told you that it was perpendicular, so that's good. Now, the other thing that we talked about very briefly on our last lecture is that torque is equal to I alpha. Torque is equal to I alpha. Remember, F is equal to ma. Torque is equal to the angular analogy to mass, which is I, times the angular acceleration, which is alpha, okay? So we're going to now set this up. We're going to say the sum of the forces, except now it's, well, we can say, okay, the sum of the torques is equal to I alpha. And our torque pulling down is our tension times our radius. Now the eye of a disc, again, this comes from page 278, is 1/2 mr squared. Also, that alpha is equal to A over R. And this comes from that equivalent. If you've got something moving translationally and rotationally, the alpha R is equal to A, therefore alpha is equal to A over R. So now we're going to put this right here, and now we're going to get A over R. Okay, now this radius is going to cancel out with one of those, and this one's going to cancel out with the other one. And now we can say tension is equal to 1/2 of our MA. And we know that our mass is equal to 5 because we switched that mass over. And now we can substitute our tension from it being 5 to 5/2. So now we're going to have 9.8 minus 2.5A is equal to 1A. 9.8 is going to equal to 3.5A. Divide both sides by 3.5. And now we can say 9.8 divided by 3.5 is going to give us an acceleration of 2.8. So our acceleration is equal to 2.8 meters per second squared. And now we can see that is going to be a little bit different. So you guys will see some equations kind of like this setting this up. But essentially, we have the sum of the forces or the sum of the torques, and we can see how things cancel each other out. That are essentially they're the same thing. All right. So we will see you next time.